Hello everybody, and welcome back to another geometry question taken from an Olympiad a few years ago. So let's get into the question. Okay, let's just zoom in a bit more. The diagram shows three squares with centers A, B, and C, and point O is a vertex of the two squares. We need to prove that OB, which is this line, is perpendicular to CA, which is this line. Okay, so to prove that two lines are perpendicular, we'll need to think of them in terms of like lines on a graph, if that makes sense. So if we just consider these shapes that will be on a graph with the point O as the center, let's just label it as 0, 0. So now let's just find out what A, B, and C all are in terms of this. So we don't know some of the length, so like, let's just make this length C, this length A, and this length as B. Okay, so the relationship which we have between A, B, and C is that if we just extend this line up here, and likewise with the other two, we can prove that, well, not really prove, we can derive that 2C equals 2B plus 2A, meaning C equals B plus A. Okay, so now that we know that C equals B plus A, we can hopefully move forward a bit in our question. So now we can express point A, B, and C. So let's do that. So point A equals AA. Both its horizontal and vertical components are A. Point B equals, okay, so its horizontal component, x component, I should say, is B, and its vertical component spans across the entire length of square A, so it's going to be 2A, plus the vertical, half of the vertical height of B, which is going to be B. And now point C equals C as its vertical component, and negative C as its horizontal component, because remember it's going in the other direction. And point O is 0, 0. We'll just write it here because it will help us with the future part of this question. So now we need to find out the gradient of AC and BO. So let's start off by working out the gradient of AC. So the m of AC equals the change in x divided by change in y. So it's going to be, let's start off by the y component of A. So we get A minus C divided by A minus C. And if we just move that over here, we get left with A minus C divided by A plus C. So we'll just leave this like this, and then we'll carry on by working out what the gradient of BO is. So m of BO likewise equals the change in x divided by, the change in y divided by the change in x. So that's going to be 2A plus B minus 0, but I won't write that since that's nothing, and B minus 0. So now let's just try and write this in terms of A and C, because remember we're trying to derive a relationship between the two gradients. So 2A plus B, so A plus B equals C, therefore if we just write C plus A as the numerator, and as the denominator we get C minus A. So now as you can see that this has a clear link between this and between the top gradient. So now let's just prove that these two are perpendicular. So if two lines are perpendicular, then their gradients multiply to give -1. Therefore A minus C divided by A plus C times A plus C divided by C minus A So now let's just see what this gives us. So a plus c and a plus c from both fractions cancel out. So we get left with a minus c divided by c minus a, which equals -1, but I'll just prove it in case you don't quite see it yet. So this can be rewritten as this, the numerator -1 c minus a, because we have a negative c in the numerator, which is covered by negative c, and positive a, and two negatives multiplied to get a positive, divided by regular c minus a, which just simplifies down to -1. So therefore, if we go back to our question, we've proved that the two lines are perpendicular. So let's just take that part off the question. And now we need to prove that they are both equal. Okay, so to do this, we have a variety of methods which we could use, I guess. So what we could do is we could work out what each of the hypotenuse lengths are. That's going to involve a lot of effort, because if I just draw these right angle triangles here. Okay, so to work out the magnitude AC, we'll need to effectively multiply, we'll need to use Pythagoras' theorem, so we'll need to work out the vertical component, square it, then horizontal component, square it, square root the whole thing, and we need to do that for both triangles, and then, like, we don't even know if we're going to get an answer after all that. So another way which we could do it is we could prove that both these triangles are congruent. Because if they're congruent, then their hypotenuses have to be equal. That's just how it works. So let's just try and prove that these two are congruent. They already have one congruency condition, which is that they're both right angle triangles. So if we can prove that the hypotenuse and another side length are the same, then they're equal. But we don't want to prove the hypotenuse is equal, because that's a lot of effort. So let's try and prove that each of these lengths are equivalent. So I'm going to label this P and label this D, let's say. So let's start by working out what CP is. So CP, the value of CP is going to be C minus A, because the C is the component of the square labeled C, and A likewise with A. And now we'll basically just do the same thing with OD, and then they should, in theory, be equal. So OD equals just B, length B. And, okay, so C minus A equals B, because A, if we just scroll up a bit here, C equals B plus A. Therefore, if we're just going to be super clear in our working, B plus A minus A equals B. They're both equal B, therefore we've proved that one side is the same. I'm just going to label that side. And now if we prove that AP is the same as BD, we've proved the hypotenuses are equal. So AB equals C plus A. The reason for this is because if we just look at PA at the top right corner, top left corner of the screen. So P to the boundary of that square, that length C, and that same boundary to A is another A, so it's going to be C plus A. And if we just go up here, the length BD can be written like this. So BD equals 2A plus C. If we just go back here, similarly, if you remember, the vector component of B is also 2A plus B, because that's the same thing effectively. So yeah, that's going to be 2A plus B, not C. That was a typo, very bad typo. And okay, so again, A plus B equals C, therefore this is going to be A plus C. That is not an EO there, that is C. Therefore, both of these are A plus C, therefore that's another side which is the same. And now we have two sides which are the same in a right angle triangle. So that's a congruency condition by itself, that side angle side, remember. But yeah, I mean, if we really want to prove this, then what we could do is square both these values and work out the hypotenuse of both right angle triangles from the side length information which we have over here, and we can prove that hypotenuses are equal. Or we can just end our answer here because they're congruent by SAS, because they both are right angle triangles. Therefore, we've also proved that they're equal. So that wraps up the conclusion of this question. I hope you found that useful and hopefully you learned something from that. This was quite a tricky question because the first time when I solved it, I tried to work out the hypotenuses immediately without working out the side lengths, which was a very, very long-winded method, and it eventually got me the answer, but when I looked at the answers, it's a much simpler method. So yeah, just something to learn from this. It's probably just try and express triangles in terms of their congruency conditions, because more often than not, when you see two triangles, it's almost always going to either involve congruency or similarity, one of the two. So yeah, a learning is probably just, if you just try and scan for similarity, then this question would be much easier than if you try to work out the lengths of AC and BO. So yeah, thank you for listening, and I'll see you in the next video. Bye.